This is the beginning, I think, of a 30, 40-year run for long duration storage, but it is not ubiquitous everywhere. Where the policy is there, the amount of renewables that storage firms up isn't quite there yet. And then there's just various other policy incentives that need to get put in place for it to pencil out.
The Clean Power Hour is brought to you by the Clean Power Consulting Group. Check out all of our content at cleanpowerhour.com. Please give us a rating and a review on Apple and Spotify. That helps others find this content. We also have a great YouTube channel. Just click on the YouTube icon at cleanpowerhour.com and subscribe to the show there. Today on the Clean Power Hour, long-duration storage using advanced compressed air technology. My guest today is the co-founder and CEO of Hydrostor. Welcome to the show, Curt VanWalleghem.
Thank you, Tim. Looking forward to chatting with you today.
Super pumped for this episode. You know, long-term storage is so important to all of us in the energy transition. And, you know, at face value, you are using some very tried and true technologies, but putting it together in a unique package. So I look forward to learning more about that. And but for our listeners, would you please give us a little bit of background on yourself and how did you come to found Hydrostor?
Sure. So I'm an engineer MBA, education-wise. I then worked in the management consulting field for a decade or so, turning around capital projects. And then I joined a utility, a nuclear and wind generator. And it was there when I was doing planning where we started having turn up and down nuclear reactors, depending on how windy it was, that I realized the need for storage was going to be pretty huge. Tried to build a pumped hydro plant, realized how challenging they are to find sites. And then I met a gentleman named Cameron Lewis who had this idea for taking the conventional compressed air technology, making a couple of patented improvements to it that would make it far more appealing and improve the value proposition. So after getting to know him, I was convinced. So I left my job, put the first bit of money in, and 12 years later, here we are.
So let's just quickly review the tech, and you have some pilot projects now in the works. Well, you have an existing pilot project, but you also have some much bigger projects that are under development. But paint a picture for us, and then at some point I'll show this. Well, maybe I'll do that while you're explaining it. I can put this little video on screen that you've got on your landing page, which is quite good and explains how Hydrostor works. But in your own words, what is the value proposition of Hydrostor and what is the technology?
Sure. So compressed air, there have been multi-100 megawatt compressed air plants, Germany and USA, going back 50 years, very reliable. What we've done is we've done two improvements to it. So when we charge, we suck in atmospheric air, just like conventional compressed air. But as you compress it through the compressor, traditionally they would just waste that heat. We store that heat. So we run the hot air through a shell and tube heat exchanger, pull out the heat and store it in hot water tanks at about 200 degrees C, wrapped in insulation. The cool down air is then sent underground to what you see here, which is a rock cavern. And that's the second difference is the first is we store the heat. The second is we use these rock caverns instead of salt caverns. And the reason we do that is salt caverns are very limited, just like pumped hydro. They're not in the right place and there's not enough of them. So, but bedrock is almost everywhere. And by using this hydrostatic compensation, where you push the air in and it lifts water out, that allows the cavern to be much smaller than it would otherwise need to be if it was a fixed volume. And that makes rock mining cost competitive with salt caverns because you need 1/10 the space and it costs about 10 times as much per volume. And therefore you get roughly the same economics out of it, but you get tremendous more siting flexibility. So once the air has filled the cavern and displaced the water, a valve holds it in. And we want to discharge. So that surface reservoir holds the water that was in the cavern before we charged. Then a valve opens, the weight of the water brings the air back up. It goes in reverse through the shell and tube heat exchanger to preheat. Conventional compressed air would have burnt some natural gas and had emissions. We eliminate that. We use that heat from compression. And then we run through a air turbine, which is just like a steam turbine, just with the blades re-arrowed for air. And the air goes back to the atmosphere. So it's very tried and true. And the two tweaks, one is store air, and that's a very simple process with shell and tube heat exchangers and hot water. And then use these rock caverns, which are used in the hydrocarbon industry for gas storage, just tweaked with this hydrostatic compensation that has other uses in the sector. So we've just bundled this all together to make compressed air more efficient, far easier to site, and a lower cost. And so now we're out to have an impact on the energy transition by developing, and we're partly a developer as well, Hydrostor, not just a solution provider. We're out developing projects. Roughly 500 megawatts is kind of our standard solution with about 8 to 10 hours. We're out developing those projects across North America and Australia.
Very cool. So it seems like it uses some of the concepts from closed loop pumped hydro, but it's the hydro is just a facilitator. It's not the main driver. It's the pumped air or compressed air that is driving the turbine. Am I right in that?
Yeah, that's a very astute point, Tim. And some people have called us pneumatic pumped hydro because we use the air to lift the water in a kind of a closed loop. And the reason we do that is we use about only 5% of the space and water compared to pumped hydro. So we are far more compact and cheaper to build than pumped hydro because the air is compressible and water's not. The flip side of that, though, is we have to convert the electricity to air and then lift the water, as opposed to just electricity to pump the water. So we have about 5 to 10% lower round trip efficiency than pumped hydro. But like I say, far easier to site, permit, and cheaper to construct. So it's a complement to pumped hydro, I would say, as opposed to if you had a perfect pumped hydro site and you could build us next to it, you'd probably go pumped hydro if you could permit that much space. But pumped hydro is very tough to site. Ours is a lot easier to site.
Yeah, I love pumped hydro, and of course hydro in general is very established technology. It's just limited geographically. There are only so many places where you have that vertical differential that you need, and as well as easy access to a place to access water, whether that's a river to dam or building a reservoir.
One other quick fact on that, Tim, is pumped hydro has a lot of evaporative losses as well, right? You got the two bodies, and they are 20 times as big as ours. We don't have any makeup water because ours is much smaller. We just have one that's exposed to the atmosphere. But secondly, when you compress air, it knocks out moisture, and that moisture is equivalent roughly to the amount of evaporative losses. So we have no makeup water requirements compared to pumped hydro. So we're far more water efficient in our water balance.
And in that video that we saw, how big is that facility, and how many megawatts is that facility in the video?
Sure. So that's obviously a rendering. It could be a range of different sizes. To give you a sense, our 500 megawatt, 8 hour, so that's 4 gigawatt hours per cycle of electricity, project in California, Kern County, takes up about 50 acres. And that's everything. That's the surface pond, the building, the noise buffer, parking lots, everything. And the cavern is underneath it. So that's the aerial footprint. So that gives you a rough scale. You can
50
add
acres
hours
for 500 megawatts.
Yeah, at roughly 10 hours. Yeah.
Yeah, that's an awesome physical footprint, right? If it was a solar farm, it would be 2,500 acres or something like that.
If you tried to build lithium ion systems for 4 gigawatt hours, you'd probably exceed that. So yeah, it's pretty dense.
And the engineered cavern where the compressed air is being stored, how difficult is that? And the website references mining technology. I know very little about that, but how hard is that to A, I guess, site, and B, construct?
So Very easy to construct. It's kindergarten mining, if you would, not chasing an ore body. We just need some void space. And so as long as the rock is competent enough that it's not going to collapse on the workers, you can build it there. So what they do is they sink a shaft, and these are roughly 8-foot diameter shafts, and they sink them, steel line them. Then you can set up an elevator system to move people, rock, ventilation, and you lower down people and equipment. And then they just drill, blast, and muck out the rock. And they make it in whatever shape is best for the rock host. And they make a certain void space, and they bring that rock up. A lot of it is used for the berm of the surface reservoir to build up the walls of that pond. And then the rest can be stored off-site or sold. And then it's there for literally 100 years. There's no moving parts down there. It's just a hole in rock. And the delta P on the rock is very limited, because if you could imagine yourself being 2,000 feet underground, the groundwater is trying to come in and the rock is trying to collapse. And our air is pushing back at the same pressure based on the water head. And so it's like a 5-10 PSI pressure being applied to the rock, which is very nominal. The hardest use case is really when it's being constructed and it's atmosphere there. Again, you don't want the rock hole to collapse on people. That's really the most stringent case. And once you put it into operation, say very little stress on the rocks through the operating life. And there's hundreds of these caverns.
I mean, I love geeking out on these details, so forgive me. But what are you lining the cavern with?
Nothing. It's rock.
Okay.
We'll grout any fissures. They'll put up some mesh to make sure loose rocks don't fall on people when they're constructing it. But it is the rock that it holds it in. Because you can see, again, if you have a drive pressure of 5 to 10 PSI and you're 2,000 feet underground in bedrock, how it's going to take an awful long time for any air to find its way through with that little drive pressure, 2,000 feet of rock. And even if any did come out, it's air. It's atmospheric air. There's hundreds of these rock caverns, like 300 in the US, storing natural gas and different hydrocarbons. They tend to only build them in certain granites and stuff because they can't have any leakage. But because we're just using rock, that's what really expands our siting flexibilities. Anywhere there's competent bedrock, you can put one of these.
Yeah, most people don't realize that they probably live in proximity to some kind of a storage cavern. Here in Central Illinois, we have natural gas caverns, or they're caverns that are being used to store natural gas. But some of them are not without their challenges when it comes to natural gas storage. But if it's just air, it's completely harmless, right? Natural gas can leak out of these caverns and then get into the water system and so forth of communities. But all right, well, let's
just on that, Tim, because I kind of like nerding out on these things too, is when because they can't put natural gas in contact with water to do this hydrostatic compensation stuff that we do, they tend to over pressurize, right? So they're putting it almost like in a scuba tank, right? You're pumping in more gas and it's stressing the rock. For us, it's almost in symbiotic balance, because the groundwater is trying to get in at roughly the same pressure as our water head, and the air just flows it up and back with minimal stress on the rock, and the pressure doesn't really change on the rock. Whereas in that gas storage, you have high pressure at certain times of the year, and then when they deplete a lot of it, the pressure really drops, and that pressure fatigues the rock. We don't do that, so it's a far easier use case what we do.
So 500 megawatt project. What is the application that you're working on in particular in this first one in California?
Project in California, there's a mandate for them to acquire 8-hour backup power called resource adequacy, and so part of the revenue comes from that, where an off-taker or a load-serving entity would contract for the resource adequacy. And the balance of the revenue comes from arbitrage, buy low, sell high, and you can provide a few ancillary services as well. But our revenue stack looks quite a bit different than the lithium-ion batteries, which are really heavy into frequency regulation. We have virtually almost no revenue from that source. We're much more arbitrage, standby power, resource adequacy, is really the business case there. We also have a project in Australia, 200 megawatt 8-hour. There it's a little bit different, but not that much. We have a contract from the transmission company to provide reliability services to the grid where they used to have diesel gensets. So now we provide that service and take out the diesel generators. And then we do arbitrage to balance the rest of the revenue. So, but mostly arbitrage, backup power.
Hey, everybody. Thanks for listening to the Clean Power Hour or viewing it on YouTube. We do have a great YouTube channel. If you're not subscribed, please go to cleanpower.group and hit that YouTube icon and subscribe to our channel. Of course, you can find all of our content on your favorite audio platform as well. So please give us a rating and a review. Back to the show. Seems like a great application for remote mining operations, which struggle to go green, so to speak, right? Because they tend to be out in the middle of nowhere. And then you don't really have a grid necessarily, but I'm just curious. Like when you think about the suite of good targets for your technology, what is the lowest hanging fruit?
Yeah, so you would think that it would be those off-grid mines, and we are working on a few of them. The challenge there is, ours is a 100-year asset when you build it. 50, 100 year, kind of pick your number, but you can keep running it in perpetuity. These mines often will get approved for a 12-year mine life and then extend it and then extend it. And so they can't really commit to a really long time frame. Secondly is their load requirements. Quite often, they're just not big enough for us. That's one of the drawbacks of our solution, as well as pumped hydro, is we kind of need 200, 300, 400 megawatts at a minimum to build. Otherwise, it just doesn't justify going to all the effort to build out the cavern. And so a lot of these mines just don't need that amount of power at their site. And when you think about the amount of solar and wind to power a 400 or 500 megawatt storage system, now you need an awful lot of land for wind and solar as well, if it's all going to be co-located. So, we don't see as many of those massive ones unless it's a massive processing center. So what we really do is we target regions that have high renewables and are trying to decarbonize and don't have lots of cheap gas or don't have a policy against gas to firm up those renewables. So right now, Australia, United States, and a few other markets around the world are attractive to us, but more and more as renewable penetration ticks up, more and more markets are coming into the money.
And as far as, you said something that is a little bit of a sore spot for me, and that is penetration, right? We have California and Hawaii with high penetration, but relatively low penetration in pretty much the rest of the U.S. still. I think our national average is on the order of 5% for solar, say another close to 10 for wind, and But besides California, are there specific states where you are looking for opportunities?
Yeah, there are up in New York, Arizona. So our team's actually going through a bunch of that analysis right now. And there's some that are almost there, others where the state market isn't quite there, but there's opportunistic opportunities where a certain coal plant is being shut down and they need replacement capacity. But yeah, it's when I remember when I started Hydrostor, that was when 15-minute batteries were just starting to come out in the PJM market. And when you have very little amount of storage or renewables, you don't need any storage. And then you need a couple of minutes, and then it stretches to half hour. Not many places need 8+ hours of storage yet, but they all know it's in their future. California's leading the way. Australia's leading the way largely because they don't have the gas. They got coal, which is very inflexible. And we're now starting to see opportunities, like I say, in markets like India, UK, Ireland, certain Western European countries. So this is the beginning, I think, of a 30-40 year run for long duration storage, but it is not ubiquitous everywhere. Where the policy is there, the amount of renewables that storage firms up isn't quite there yet. And then there's just various other policy incentives that need to get put in place for it to pencil out.
It does seem like power plants that are transitioning, we do have a large fleet of coal and natural gas power plants that are in the process of being phased out. Here in Illinois, we have even legislation specific to this phenomenon called coal to solar, where Vistra is going to replace a fleet of coal plants with solar and batteries. Are you getting traction with the utilities that are, that own these power plants and, planning for a more economic future?
Yeah, we are. What I would say is there's some integrated utilities where everything gets rate-based. They don't have quite as much flexibility to try out newer technologies that are scaling up. So I think, and again, we're a developer, so we're out in these deregulated markets, securing contracts, project financing, and building our own, like in California and Australia. And as we have success doing that, it makes it easier for a big integrated utility to go to their regulator and say, we want to buy one of these and replace this coal plant. But it's a little challenging for them because, again, our projects are pretty big. They're, call it $1 billion each. There'd be quite a bit of scrutiny, as you can imagine, a utility trying to rate base something. And if anything didn't work out, that wouldn't be very good for them. So I think it's best that we do our deregulated path, working on a few of those where we replace coal plants and repurpose that interconnect. I think they're going to want to see success elsewhere before they contract for it.
What are the economics? What are the, barriers to entry for Hydrostor? Why have things kind of just come together now, so to speak?
Not really any barriers other than what every new technology has to go through. I mean, if I look at our 12-year history, invent the technology, raise venture capital, build a 1 megawatt pilot, and test it for 5 years. In parallel with that testing, we get a 10 megawatt hour contract, commercial contract, build a bigger pilot to put that's been running for 3 years. And with that, we got the ability to wrap and performance insurance for our process. So then in parallel with running that commercial plant, build a development team, raise a bunch more money. We're backed by Goldman Sachs and CPP, and go secure interconnection, land, get permits to build this 500 megawatt and 200 megawatt and secure the contracts there. And now we're driving to financial close. So in the large scale energy infrastructure space, nothing moves that quick. Everything requires a few years of permits. Interconnect takes 2 or 3 years. And you kind of got to sequentially go through pilot, small commercial, get insurance things put in place, develop and drive to bigger plants. So we've just methodically kind of worked through that plan, and we'll be driving to financial close on roughly 700 megawatts of plants towards the second half of next year.
The Willow Rock project in Kern County, this is in Southern California. It sounds like a wonderful project. I'm just curious, though, where exactly is it in development and when are you breaking ground?
Sure. So that project, we've announced that we're data adequate with the CEC, which is the permitting jurisdiction. So that means they have all the information, and there's a timeline commitment for the end of next year to have all the permits in place, unless, of course, there's some reason for them to delay that. And that's really driving the critical path is the permitting. So we expect that roughly at the end of next year, which will allow us to go to financial close and start construction. The interconnect, we've confirmed we have the interconnection and the full deliverability. We've got the land, all the engineering and borehole work has been done. And we expect to be announcing contracts starting in Q4 of this year for that facility.
Yeah, I think I even saw a post that you're working with Kiewit on some of the engineering.
That's right. Yeah, Kiewit's the EPC provider doing the front-end engineering and, I guess the lead horse to do the whole construction, but we kind of commit phase by phase to make sure the partnership is working out. But so far, so good. Really happy working with them.
And then when you think about the ecosystem of energy in the United States, who are good partners, and who do you want to hear from moving forward, who might be listening to this podcast, who should know about Hydrostor and who's a good partner or customer?
Yeah, so Customer, anyone looking for long duration, as long as you've got large needs, again, above hundreds of megawatts for a single project site, we're a good fit. Obviously, if you only need 10 or 20 megawatts, you're probably looking more like a flow battery. Partners, anyone with interconnects, it is really tough to get 400 or 500 megawatts of deliverable interconnect on the grid. So a lot of developers out there with interconnection and queue positions. If you think it's a good fit for storage in a market, we'd love to hear from you. Team up to develop it on their site at their interconnect position. And then we use union labor. We buy steel. We buy rotating equipment from the major OEMs, be that Siemens, MAN Turbo, Baker Hughes, Mitsubishi, the wide range of equipment OEMs. And then the EPC community that we lean on, like Kiewit mentioned earlier, to build the facilities. We're also always keen to talk to debt providers and project equity providers. Our business model is we're the developer solution provider, and we put some of our equity into the project, but we look to bring others, whether it's pension funds or other IPPs to co-own, or infrastructure funds to co-own the projects with us. So pretty large set of groups. And now with the IRA passing in the US, there's also tax equity partners and folks that may want to monetize certain tax credits and get associated with the project. So no shortage of people to work with.
And this may be a sensitive topic, so forgive me, but on a price per watt, large scale solar, we're at about $1 a watt, give or take. Can you give us a reference point for Hydrostor on cost of construction?
Yeah, we're being the $2 to $2.50 a watt. I would say on a fully installed, insured basis for a 50-year asset that never degrades, would be roughly the ballpark. And that's pretty compelling vis-a-vis other storage solutions like pumped hydro, certainly lithium ion. You couldn't build that 10-hour duration for that rate and wouldn't have anywhere near the longevity. And then when you start getting into the long duration sector, whether it's flow batteries, thermal, compressed CO2. I know you had Energy Dome on not long ago.
Yep.
You look at the basket, there's really a whole bunch of different variables that come in, whether it's land footprint, minimum sizes, round trip efficiency, life of the asset, all those, and there's a role for a lot of different solutions, but we're kind of the bulk, very good performance on efficiency, long life, and then really low cost, probably lowest cost of the sector on a fully installed basis.
Well, is there anything else our listeners should know about you or the company? I'm super excited to see you guys come out of the ground literally with a 500 megawatt project in Southern California. I wish you the best with that. And it's sorely needed. Long-term storage is just one of the big holes in the energy transition right now that people are trying to figure out. So it's great to see such a clean and tidy solution as Hydrostor. I'm really grateful.
Excellent. Well, it's been great, Tim. And I guess the only closing thought, this energy transition is a massive undertaking. We got to triple the size of the grid and replace that 80% of thermal with clean resources, and transmission access, permitting reform to allow stuff to go quicker. Because you look at a pumped hydro project or ours, it takes longer to permit it than it does to construct it. We got to figure this permitting stuff out and building out the transmission system if we're going to be successful in the energy transition. So encourage people to talk to their senators, their representatives to get the policies put in place to allow us, because it's not technology. We've got that solved. It's not money. There's more than enough money waiting to do it, and the ambition's there. Now we just need the regulatory and the bottlenecks, the red tape to get out of the way, and that's often done at the ballot box. So encourage people to vote and vote for folks that get behind the energy transition and help us make it happen.
Well said. Well said. Well, check out all of our content at cleanpowerhour.com. Please give us a rating and a review on Apple and Spotify so that others can find this content. We need tens and tens of thousands of more people to come into the clean energy transition. Reach out to me. I love hearing from my listeners. And I have a series of trainings now on HeatSpring, so check out my trainings on heatspring.com. I'm Tim Montague. Let's grow solar and storage. Curt, how can our listeners reach you?
We're at hydrostor.ca, or you can email me directly, Curt, C-U-R-T, at hydrostor.ca.
Wonderful. Well, thank you so much and have a great day.
Excellent. Thank you, Tim.